Hello everyone, Bill Nye here, and I'm thrilled to take you on a fascinating journey today. Today we're diving into the intricate and captivating world of engineering curves, where precision meets creativity. We all know circles, squares, and triangles. These are the basic shapes that form the foundation of so much of what we see around us. They're easy to define and build with, but real-world designs often require more than just straight lines and perfect arcs to truly come to life. Enter complex curves and splines, the unsung heroes of modern design. Unlike simple shapes, splines are free-form curves, essential for creating modern, efficient, and aesthetically pleasing products. Think of the sleek body of a sports car, or the wing of an airplane. These are smooth, flowing surfaces, not just straight lines or circles. These shapes are defined by splines, mathematical curves that are controlled with incredible precision and detail. Learning to read and create these curves is a key skill in advanced manufacturing, automotive, and aerospace engineering, where precision is paramount. It's how we turn complex ideas into reality, transforming concepts into tangible, functional objects. In this guide, we'll explore what splines are, how engineers create them using CAD software, and how to interpret them on technical drawings. We'll look at the notes and tables that give these curves their exact form, ensuring accuracy and functionality. A tiny mistake in reading a spline can lead to big problems, affecting the entire design process. So let's move beyond the basics and embrace the complexity of the curve. Ready? Let's get started on this exciting adventure. What's the difference between a simple curve and a spline? It's a question that comes up all the time in engineering and design, and understanding the answer is key to mastering CAD and digital modeling. A simple curve, like an arc, is just a segment of a perfect circle, defined by a single radius. This means every point along the arc is exactly the same distance from the center, making it mathematically straightforward and easy to work with. It's predictable and easy to describe, perfect for things like pipe elbows, rounded corners, or any feature where a constant curve is needed. These shapes are everywhere in mechanical parts because they're reliable and easy to manufacture. But a spline is something else entirely. It's a different kind of curve, one that can be as simple or as complex as you need. The term comes from shipbuilders who used flexible strips, called splines, to draw smooth curves through a set of points on their blueprints. These physical splines would naturally form the smoothest possible path, connecting all the points in a gentle, flowing line. Today, splines are mathematical curves, defined by a series of control points. In digital design, these control points act like anchors, shaping the curve's path with incredible precision. These points guide the path of the curve, allowing it to bend gently in one area and tightly in another. The more control points you add, the more detailed and flexible your curve becomes. In CAD, the software uses these points to create the smoothest possible line, automatically calculating the best path through or near each control point. This makes splines ideal for complex shapes in organic forms. Unlike a simple arc, a spline can change its curvature continuously along its length. This means it can flow smoothly from tight bends to gentle sweeps, all in a single curve. The real power of a spline is flexibility. Move one control point, and you can tweak just a section of the curve, leaving the rest untouched. This local control is a game changer for designers. Designers can sculpt shapes with incredible precision, refining them until they're just right. Whether it's for automotive bodies, consumer products, or architectural details, splines let you fine-tune every contour. With a simple arc, you get one control, the radius. That's it. The shape is fixed and can't be adjusted beyond making the arc bigger or smaller. With a spline, you get many. Each point is a handle for shaping the curve. You can add, move, or remove points to get exactly the shape you want, no matter how complex. This is what makes splines so powerful in modern design. They're the secret behind the smooth, flowing lines of everything from cars to consumer electronics. It's like being a digital sculptor, molding a line instead of clay. The possibilities are nearly endless, limited only by your imagination and creativity. Splines give us control and creativity. That's their magic. They're the bridge between technical precision and artistic freedom in the world of digital design. Now that we know what splines are and how they work, you might be wondering, where do we actually find these wavy lines in the real world? The answer is almost everywhere, especially in the design of advanced products and technology that surround us every day. Take a look at any modern car. The hood, the doors, the fenders. None of these are just simple, flat panels. Instead, they're made from complex, flowing surfaces that give the car its unique look and feel. These beautiful aerodynamic surfaces are created using intricate networks of splines. Splines are absolutely critical, not just for the car's appearance, but also for its performance on the road. The exact shape of a car's body, defined by these splines, determines how air flows over it. This has a huge impact on things like fuel efficiency, speed, and even how quiet the ride is. Engineers spend countless hours tweaking and refining these curves in digital wind tunnels, searching for the perfect balance between style and aerodynamics. In aerospace, splines are just as important. They define the cross-section of an airplane wing, which is called an airfoil. The airfoil's shape, made up of hundreds of precisely placed points, is what generates lift and keeps the plane in the sky. Even the tiniest error in the curve of a wing can have a dramatic effect on flight performance, safety, and fuel consumption. Splines also shape the fuselage of airplanes, making them both aerodynamic and strong enough to withstand the forces of flight. But splines aren't just for big, high-tech machines. You'll find them in everyday products all around you. The comfortable, ergonomic shape of a computer mouse or a power tool handle is carefully crafted with splines, so it fits perfectly in your hand and reduces fatigue. Designers use splines to create the sleek hulls of boats, the efficient blades of fans, and even the smooth, protective cases of smartphones and tablets. These flowing curves are like the hidden language of modern design, shaping everything from the things we drive to the gadgets we use every day. So, whenever you see a smooth, organic shape, whether it's in a car, a phone, or a kitchen tool, you can be sure that splines are at work behind the scenes. Splines make products not only more efficient and comfortable, but also more beautiful and enjoyable to use. They truly are the secret ingredient in the art and science of modern design. So, how do engineers create these curves? With computer-aided design, or CAD. In CAD, engineers place control points to outline the shape they want. The software connects these points with a spline, using advanced math to create a smooth curve. If the shape isn't right, just move a point. The curve updates instantly. Some splines pass directly through each point, others are pulled toward them, giving designers flexibility. Engineers can also set constraints like making the end of a spline connect smoothly to another line. This ensures seamless transitions, critical for things like car panels. The CAD software handles the math, so designers can focus on creativity and function. With CAD, creating and refining complex curves is interactive and precise. It's the backbone of modern design. That's how splines come to life. Creating a spline in CAD is one thing, but how do we communicate that shape for manufacturing? Since splines don't have a simple radius, we use control points with exact X and Y coordinates on engineering drawings. Manufacturers use these coordinates to reconstruct the curve in their machines. Sometimes, drawings include notes about the curve's degree or tangency, how it starts and ends. To keep drawings clear, engineers often use a separate table listing all the points for a spline. The drawing might say, "See Table 1 for definition," and the table provides the data. This keeps the main view clean and the data organized. Reading these drawings means connecting the visual curve with the numbers in the table. Let's look closer at the coordinate table, the recipe for a spline. The table lists each point's X and Y coordinates, measured from a defined origin. This set of points is the blueprint for the curve. No guesswork, the number of points depends on the curve's complexity. Simple curves need a few. Complex ones might need hundreds. The goal is enough points for accuracy, but not so many that it's overwhelming. Manufacturers input this data into CNC machines, which use it to guide cutting tools or printers. The machine interpolates between points, recreating the smooth spline from the CAD model. This direct transfer from drawing to machine is what makes high-precision manufacturing possible. The table bridges digital design and physical reality. It's the key to making complex curves real. Once a part with a spline is made, how do we check it's right? Not with a ruler. Quality control uses tools like coordinate measuring machines, or CMMs. A CMM touches the part at many points, recording their coordinates. Software compares these points to the original CAD model, showing any deviations, even tiny errors, thousandths of an inch, can be detected. For quick checks, inspectors might use profile gauges, templates cut to the spline shape. These aren't as precise as CMMs, but they quickly spot big errors. Inspection ensures the part matches the design, every curve accounted for. Splines are everywhere in engineering. Jet engine blades and turbine airfoils are defined by splines for maximum efficiency. Ship hulls use splines for smooth, hydrodynamic shapes, now designed in CAD, not with wooden strips. In medicine, custom implants are modeled with splines to fit a patient's anatomy perfectly. Even plastic bottles use splines for strength and shape, preventing weak spots. From massive ships to everyday bottles, splines make designs efficient and strong. They're the unsung heroes behind products we rely on. Without splines, modern engineering wouldn't be possible. They turn creative ideas into real-world solutions. Why does all this matter? Because precision with splines is critical. A small error in a spline can mean parts don't fit, products fail, or safety is compromised. In cars, mismatched splines mean doors and fenders won't align, leading to leaks and costly fixes. In aerospace, a tiny error in a wing spline can affect lift, efficiency, or even safety. Drawings are contracts, splines, control points, and tables are the language. Everyone in manufacturing must be fluent in this language. Gadeti genauers and gum curves $1 means safer, better products. It ensures the digital vision becomes a physical reality. That's the power of splines in engineering, and that's what great engineering is all about.